Hey everyone. So today we're going to talk about Connectionist temporal classification. This is something that we went over in lecture 13, but today we're going to take a more practical look at it. We're going to go through some code, and specifically, this is a visual demo, and I hope that you can take some of the lessons from this and apply it to your homework, which is a speech application of CTC. But first, let's do a review. So when are we going to use CTC? Specifically, we are going to consider a set of many-to-many sequence prediction problems. In these problems, we have a series of inputs, and for each input, we are going to produce an output, and each one of these outputs is going to be based on all of the previous inputs before that output. And in these problems, generally, the labeling order matters, but there's not necessarily a one-to-one correspondence between outputs and labels. So an example of this is speech. And in speech, we can have variable length speech recordings. And even if we constrain the problem to equal length speech recordings, there is variability in the sounds, in the specific phonemes. So even if we have two of the same high-level labels, such as someone saying the word dog, and we output a prediction at each frame, it's not necessarily straightforward how we can provide labels for each frame if we just know that a specific word or set of phonemes is present in a given speech recording. So for the third reason, even if we have a label for each output, we may need to impose a structural constraint on the output sequence. So going back to homework 1, you can remember that we had these subphoneme sequences, and there was a restriction on them that there were for each phoneme there are 3 subphoneme states. You can transition from S0, the first subphoneme state to the second phoneme state to the third, and then from the third to any of the other starting subphoneme states. And we can actually use CTC to apply this constraint to training our recurrent neural networks. Okay, so now let's get some intuition for the CTC loss. And I'm going to talk about this in the method, the constraints that are placed on the output that the paper authors use, but this is not necessary exactly. I'll talk more about this later, but just remember that this is the most common setup and exists in most of the accelerated frameworks for CTC, but know that other constraints can be placed for other problems. So specifically, we're going to have a set of labels. Think about this. This could just be the alphabet, and then a labeling is going to be a sequence of these labels. And so right now, we're going to add a blank symbol to our set of possible labels. And then we're going to design the network such that at each output, we output a classification of one of these labels. So we're going to have a sequence of labels, and then we're going to collapse this sequence, with the rule being that repeated labels all collapse to that singular label, and this includes the blank. And you can see here in the last example that the blank is used such that we can have ground truth labelings with repeated labels. That's the use case for the blank here. And at the end of the day, we can compare our collapsed output with the ground truth label. And I'm going to call these output sequences paths. And it's important to note that for every labeling, there are many paths that can collapse to that labeling. But for a given path, there is only one labeling. Okay, so let's look at a practical problem right now. So consider handwriting recognition. So here we have a bunch of images. They are of equal width, equal height, but they contain variable numbers of characters. Characters can be at different positions. So the idea is that we extract some feature representation from this that preserves the relative spatial information of the different characters, and then we pass from left to right those features into an RNN, and we will output a probability distribution over characters, and say we take the character with max probability at each step, and with random initialization, we get this output, which collapses to this long thing, which is obviously pretty far from the ground truth. And the goal is, after training, we may produce some path that collapses to the ground truth. Okay, so what we saw is that the network outputs a probability distribution over all the possible labels and the blank symbol. The idea is that if we sample from all of these distributions independently, we want to maximize the probability that we will get an output sequence that collapses into the ground truth. So the idea is that this loss is really just the negative logarithm of the probability that I just described. So we can describe what we've been talking about a little bit more formally. So let's let L be the set of labels, and L prime be the set of labels that include the blank. So for a sequence T, we can now denote the set of possible paths as pi, where the size of pi is L prime to the T. So given a sequence of inputs, x of I, and a labeling, z of I, where we constrain the size of the labeling to be less than the size of the input, and we assume that the size of the input is the same as the output sequence. So denote the probability of a given labeling as P of z given the input and some parameters, and these parameters are going to be our recurrent neural network, and we're going to do the maximum likelihood estimate of all of the probabilities over all the labelings in our data set. Okay, so now we can talk about that collapsing function that we mentioned informally before. So let's define this many-to-one map B, which maps from the set of all possible paths to the set of labelings. And so B is performing this collapsing operation, which we defined before, and you can see in this example here. But we're also going to define B inverse. And B inverse is now a one-to-many map. So it goes from a labeling to all the possible paths that will collapse to that labeling. And we can think of, now we can denote the likelihood of a given labeling as the sum of the probabilities of all these paths that collapse to Z. And we can notate that as the paths come from B inverse of Z. So now we can put these all together, and we can plug in what we found for P of Z, which is the sum over the probabilities of all the paths given the input sequence in our parameters to get our maximum likelihood parameter estimate. We can take the log, which results in a sum, and then finally, so this can work with our gradient descent optimizer, we just can take the negative of that, and now we're doing minimization here. Let's try to compute the probability of a given labeling by summing over the probabilities of all the paths that could collapse to that labeling. So a naive way to try to do this is to generate all the possible sequences with their probabilities, then we can collapse each sequence, and then we just sum the probabilities of those that collapse to the correct value. So let's put this in numeric terms. Let n be the number of inputs, n the number of labels, and then c is the size of L prime. This yields a computational complexity on the order of c to the m times m. So obviously this is exponential in complexity and not very ideal. So there is a better way to do this, and we can actually derive a recursive formula for these probabilities and then exploit the existence of common subpaths. And this is generally the reason why we call these paths. And there are dynamic programming algorithms there to do this in much less than exponential time. So in lecture 13, the professor goes through this in much more depth and talks about the possibilities of other constraints that you can place on the sequences and then solve efficiently with these dynamic programming methods. Luckily for us, we're going to be using tools that implement these optimizations and often do it in a low-level language. So we can pick up this speed and these good time guarantees. So now the question comes to, what do we do at test time? So right now we have a trained network. We're going to output a sequence of probabilities, and we may just hope that by taking the max probability at each step and then using those labels and then collapsing them using the function b, we may get a good result, and we might. But this is generally a greedy approach, and it just does not guarantee that we will get the most likely sequence of labels. So there is a more intensive algorithm to determine the true answer of this, but we can also run an approximate search, a beam search, which is a method where we can keep track of multiple best paths, and we can just iterate over these to reduce the greediness of our search, but not exactly come to a exact answer. And this is generally what we're going to use and suggest that you use in your assignment. So in fact, the formulation that we've just described is not the only formulation of CTC that exists. The setup in which we introduce a blank character and design this collapsing function from the set of possible outputs to the set of labelings is actually just what's described by the original paper authors. And the CTC loss doesn't limit us to that. And there are actually other ways that we can place constraints on our outputs that are useful that don't follow this method, even though that the methods that we've described are very common and implemented natively in some of the frameworks that we're going to use. So for example, we can get rid of the blank. I mean, if we can guarantee that the same label can't occur twice in succession, which is the case for some simple varieties, then we can just create a version of CTC without blanks. And there are times when it could be useful to have many different kinds of blanks, perhaps one for each possible non-blank symbol. And we can even follow certain finite state machines. So consider in homework 1, which we actually described before, where there are 3 subphonemes per phoneme, and there is only non-zero probability of transitioning from the first to the second subphoneme, from the second to the third subphoneme, and then from the third to the beginning of any triplet. And CTC can actually apply these constraints to the output sequence. Practical problem that we're going to apply CTC to is a handwritten digit recognition problem. We have a data set of images, each one containing a sequence of digits. For now, to simplify things, it's going to be a fixed number of digits. We're going to pick 10 per sample. We're also going to constrain the size of each image to 172 pixels wide and 36 pixels tall. So the goal is that given an image, we're going to output the correct digit sequence. And interestingly, these digits can overlap, and they are handwritten, provided from the MNIST dataset, which I'm sure you're all familiar with. You may note that there are some constraints placed on this problem that are not there in homework 3. So for example, we know that there are 10 digits per labeling. And we also are not dealing with variable size sequences. So every sequence here is 172, though we may build a feature representation using a CNN that will bring it down to some width, but that is fixed. So at the end of the day, there will be a fixed length fed into our RNN for this problem. But even with these constraints, this demo will still be very informative for how you can get started implementing your CTC component of homework 3. Now let's take a look at the code. So in order to solve this problem, I've prepared a Jupyter notebook, which imports some code in a Python source file, which I call ctcmodel.py. You can find this notebook, CTC Handwritten Digit Reader, in the tutorials repository on GitHub. This is Recitation 8, so you can pull it up. There's a README for how to download the prerequisites. A quick reminder that this probably will not work on Mac or Windows. You will need a Unix system because we're going to need to install some third-party libraries, one for the CTC loss and the second for the CTC beam search decoding. Both those things need to be built, and generally I've run into a lot of issues installing on Mac, and I would probably expect the same for Windows, although I definitely recommend you give it a try and let us know how it goes. So right now, in this Jupyter notebook, We can generate the data set if it doesn't already exist. We can load the data, and you can see the data that we're dealing with here. We have 20,000 samples. These are 36 by 172 images, and each label is a integer sequence of the ground truth. Let's do a brief overview of the model that we've built to solve this task. So we have a standard convolutional neural network, which will take in our one-channel image, and this is going to output an embedding, which is batch size by number of feature maps, by the height of each feature map, by the width of each feature map. So what we want is we want our RNN at each step to take in a single column of the feature map from left to right. So what we're going to do is we're going to reshape our embedding such that we have batch size by feature maps times the height by the width. So now we've done is we've taken each column and we've strung them out. We've basically concatenated them. And now what we want to do is we want to permute the axes. That way our input is amenable for the PyTorch LSTM implementation, which expects a tensor of number of time steps. The dimension is the number of time steps, batch size, and then the feature size, which is going to be 32 times the height of our feature maps. Then we're going to feed that into our LSTM, and we're going to get logits for each time step, which will be the width of our feature embedding. So let's go ahead and run this. And this will run for about 20 epochs. Okay, so I'm going to speed up training here to make this a little bit more bearable in the video. But as we watch this thing train, notice that the value that follows eval is is an error metric that is called the Levenshtein distance. And the Levenshtein distance is basically what you can think of as an edit distance. So given two strings, how many edits do you need to make on one string to turn it into the other? So the first string is your prediction, and the output string, and the other string is your target. And the Levenshtein distance quantifies that. All right, so now we've trained the model. Now we can use our bead search decoder to actually take some samples and try to figure out what digits are handwritten. So here we're going to sample 15 images from our training set, and we're going to run them through our decoder. So you can see that things are working. Even on images that have some pretty tricky overlap, you can see these two zeros here, or this 1 and this 9. And this is frankly really strange. Even me, this would be hard to figure out that this is a 4. So we can see that this is a very powerful method. It's worked very quickly. And hopefully this explanation will help you figure out where to start for part 3. Thank you.